So while we are getting, so good morning everybody. Good morning, and thank you very much for the interest over the last few days. I've had a lot of answers on my on email. Is it working? So there was a lot of interest, and I thank you very much for this interest. So the discussion was on, it's always like, coming home to your parents, and and they make you the same food again that you liked when you were a child. It's so this is a little bit like this. So we did something very, very simple last time, and there was a lot of discussion. So this is the geometry of our Monte Carlo heliport, if you want. And there was a lot of discussion and some really interesting points raised. So, for example, one of the points that was raised, I think that you are at least, I think there were 10 or so of you who have programmed this. And one of the points raised is that if delta is much larger, if this is minus delta and delta, if delta is much larger than 2, if delta is larger than 2, then you can put this thing here, because then you have something which is equivalent to direct sampling. So that was this. But today we will go into much more advanced subjects, or somewhat more advanced subjects. It will also be the occasion for me to give you a few references. So let us formulate what we are doing. We are discussing Markov chains. And I will not go into complete detail, but Markov chains is a sequence of random variables. And random variable 0 is this thing means distributed according as distributed as pi of t equals to 0, x1 is distributed as pi t equals to 1, and so on. These random variables, as we discussed the other day, are functions from some sample space It's also called configuration space, but they call it a sample space. So it's these are random variables mapped from the sample space into the real numbers. And the point of a Markov chain is defined by the distribution of x0. So the Markov chain is defined by x0. The fact that xt depends only on x t minus 1. So there is something which we call a transition matrix. P that governs how we move from xt to xt plus 1. So now, so that is all what we can say in the example. Yes? Okay, all right, so these are the do you hear me? Okay, and if you come in, so we should, Chairman, you should tell those who come in even later that they should take their shoes off when they move up. All right, so thanks again. So here we are formulating what is a Markov chain, that a principle that we have already used on the heliport 2 days ago. It's a sequence of random variables. It's also a little noisy because my voice today is bass baritone, much more bass baritone than it is usually. So it's a sequence of random variables. You have it here, x0, x1, x2, xn. And x0 is defined according to a probability distribution pi of t equals to 0, x1 pi t equals to 1, and so on. So we have a sample space omega, and as we said, these random variables are functions from the sample space into omega, into R. So now the point that we want to make, and that's where the discussion is interesting, it is usually, so the distribution pi of t exists, but is usually unknown. Unknown, except for pi of t equals to 0. There's a second exception later on. So what is pi of t equals to 0? It is our initial configuration, our initial distribution. So this is a distribution that, first of all, we know, and second, we know how to sample. We know how to sample. So in the example of this little game Markov pi, we said at t equals to 0, we start at this point up here. Okay, so this was a model. So what is the distribution of pi t equals to 0? It is the delta function at 0.11. Okay, so this distribution, so here we had pi of t equals to 0 is the delta function of xy is equal to 1, 1. So then pi of t equals to 1 is a horribly complicated distribution. Pi t equals to 2 is a horribly very complicated distribution. But then things eventually become easier because we have a transition matrix. So what is the transition matrix? Let me discuss the transition matrix. The transition matrix so the transition matrix, we'll see it very often. P, the transition matrix P is an object that has two meanings. You know why it has two meanings? It has two meanings. The transition matrix, it has two objectives, two jobs, a day job and a night job. So it has two jobs, and the first job is the following: the transition matrix is the object that connects the distribution at t plus 1 is given by the sum over b, pi of b at time t times p from b to a. Okay? So, but I told you that we don't know. So we know pi at t equals to 0, but for us it's too complicated job to compute pi of t at t equals 1, 2, 3, 4, 5. So this is kind of abstract. And the second thing is p is the algorithm. So let me spend 5 minutes on this. So what this thing here means is, so let me explain the algorithm. So BA is so I'm putting myself in omega finite, just for simplicity. So P from B to A is the probability to move from B to A if already at B. So if P from B to A is 0.4, then the probability, if we are at B, then the probability to move from B to A has to be 0.4. That means at some point we will have a random number generator which will let us make a decision to move to A or to other places, but we will take the decision to move from B to A with probability of 40% in that case. So P is the algorithm, and that's a perfectly explicit object that we can program. In fact, the dozen of you who have programmed this algorithm have in fact programmed a transition matrix. So now, if having known this, we understand this equation. Pi of a of t plus 1 is equal to the sum of b. It is so you at time t, you are at position b with probability pi b of t, and then you move from b to a with the probability p from b to a. So this gives you the probability at time t plus 1 to be, shoes off, gives you the probability to be at position a at time t plus 1, given that you are at t. Okay, so that is the transition matrix. And this condition up here is what we call the global balance condition. Global balance condition. And it has absolutely played, so that's why I'm speaking to you about second Markov-chain revolution. So it has absolutely played almost absolutely no role in the theory and practice of Markov chains. And for example, I wrote a book some years ago, as I told you, and this equation was of course, oh no, excuse me. This is nothing here. So now, let me write down the global balance condition. Excuse me. So you suppose in the limit t going to infinity that pi a of t plus 1 or pi of t plus 1 is the same as pi of t for t going to infinity. Excuse me. I was getting ahead of myself. So then if you impose a steady state condition in the long time limit, and this steady state condition is pi a is sum over b, pi b times p from b to a. That is the global balance condition, excuse me. Condition. So it's the stationarity condition for the probability distribution. And I just told you, excuse me, so this condition, this is a necessary condition. This is the necessary condition for the transition matrix to give me so now I think, so come in, yes. Please come in. So this is the stationarity condition. This stationary condition is a necessary condition for the Markov chain to have a steady state, which is given in the limit of t going to infinity, which is given by pi. So as I said, for example, in my book, this equation didn't have a number because people generally considered it useless in practice. So now, let us do. I will get later today. I'll get into algorithms as we did last time, just for everybody to have something to do. And the transition matrix, I will just, I'll not go into detail. So the transition matrix P has to satisfy conditions. Satisfy 3 conditions. So the first one is the global balance. So global balance, here again, pi a is equals to sum over b, pi b, p from b to a for all a. So b in sample space for all a in sample space. All right. Okay, so this is a necessary condition for the steady state. There are 2 other conditions. Second, P has to be irreducible. So what irreducible means that in the example is that in the limit pi to the power of r, ab has to be larger than 0. So there must exist for all a and b, there must exist an r such that PRAB is larger than 0. That is called irreducibility. Okay, so what it means, vulgo, in usual words, is that you have to have a finite probability to go from any A to any B after a certain time. So if there exists an R for any A and B such that PAB of R is larger than 0, then the solution pi is equal to pi times P is unique. So I will not go into a complete proof of all of this. So if you are irreducible, then the solution pi is equal to pi p, which we can also write in like this. It's exactly the same equation. Then it is unique. So now we have the third condition, that p has to be aperiodic. I will explain that in 2 minutes. And if it's aperiodic, what it means, if it is aperiodic, then what it simply means is you are started A, you come back to A at some point, so you have to be able to come back to A, and the time after which you come back to A can be some time R, R1, R2, R3, and they have to be not have to be multiples of more than 1. So you have to. So if you can come back after 2, 4, 6, 8, then you have a periodic Markov chain. If you can come back at 5, 6, and 7, or at 1000, at 1001, then you have an aperiodic Markov chain. Yes. Yes, of course. Yes. Thank you very much. Sometimes I've had a big confusion. So it's so what the transition matrix raised to the power r is where you can get after r steps, and then you have to be after r steps. You have to be able to go from A to. So there must be an r where you can go to. Yes. Oh, thank you very much. We are getting, now that everybody has arrived, we are getting more lively. So that is the question. So, for example, in what we will be doing, we will impose pi. Okay, so we will impose pi. So let's say this is what I have written down has not decided on your question yet. In our application, we have decided on this question. We have a pi, which is the density matrix or the Boltzmann distribution, and we impose pi. And we are looking for transition matrices P, which satisfy this condition. So our space of experiments of algorithms, so P is, I told you, P is the algorithm. Okay? And pi is the steady state is what we impose. And so so the logic is the steady state is what we impose. That is what we know. We also know, so we know the pi to t equals to infinity. We know pi at t equals to 0. And in addition, we can sample it. So it is the delta function at 1, 1, just to fix the idea. So that's what we can sample. What is pi 17? Your whole thesis will not be sufficient to compute pi 17. What is pi 99? You don't know it. So you know pi 0. You know pi infinity, which is pi, and then you have just three little conditions. And let me tell you the following. So if p is aperiodic and irreducible, so if 2 plus 3, then p to the r, and my friend, here you are, so this is p to the r is a positive matrix for some for some r. So there will be some r, 1 million, 100 million, 2 zillions, and then p to the r will be a positive matrix. And then just 1 second, and then what happens is, in that case, p to the r, so then what will happen is that the sequence x0, x1, xn, so which means that, okay, let me put it like this, then pi as a function of t will converge to pi starting from any pi of 0. So if the transition matrix satisfies the global balance condition, if it is irreducible, if it is aperiodic, then we can start from any initial configuration and we will converge towards pi. Okay? Yes? Yes. So the steady state is unique. Steady state is unique. But we have no guarantee that we will actually converge towards it. So it's unique, but it may be, what will happen is that we will have periodic orbits, and these periodic orbits at any given time t will not will not be pi t. Yes, that's what we are doing. Yes, thank you very much. So here P is the algorithm, and we use it such that P is independent of time. So that's just the framework in which we work. We could relax that, but let's say this is maybe that's for the third Markov-chain revolution. Okay, so now we are discussing the second Markov-chain revolution, but so then in 20 years we'll all come back. You'll be my colleagues, we'll teach courses together, but that is not yet, that has not been found very useful. So let me do one little thing here. How are we doing with time, Mr. Chairman? You shouldn't talk to me like that, because then I will abuse it, okay? So, so we have a strict time budget, but we do still have a positive budget. Is that what you say? Okay, anyway. All right, so now we have plenty of time. So let me go into a subject that I will just make one little theorem. I think it's the only theorem that I'll explain to you. It comes out of it was found by Aldous and Diaconis. So this it can be looked up in. So this is this is a book. You still know what the book is, right? So this is a book called Markov-chain in Mixing Times, written by Levin, Paris, and Wilmer. I'm very proud of it because this book once belonged to a famous mathematician called Percy Diaconis, and now it's mine. So this is the book. Well, he gave it to me, so now I'm very happy. So anyway, in this book is a theorem that I want to explain to you, and it comes out of the discussion that I had in the summer school. Now we are winter school and we are all sick. I was teaching in the summer school in Bégourieu in France. So then it's this famous sailing summer school. So then nobody is sick, but everybody's tired because they fall off the boats in the afternoon. So, and people were so interested in a subject that I finally pulled out this theorem and explained it to you. So now let's do the following. PAB is irreducible. Okay, for those who come here because they wanted to have algorithms, I will tell you we have 4 fantastic algorithms a little later, but you have to wait, and you take your mal en patience, as we say in French. Irreducible and aperiodic. So I want to explain to you two things. First of all, why is it that we actually converge? So that's what I explain. And then I want to explain that eigenvalue analysis that in physics you have a transition matrix, you will be opposed to me, you say, because it's not a transition matrix, it's a transform matrix. And then you will also be opposed to me because I write it from left to right. So that's usually, but then we usually agree that we have to do an eigenvalue analysis, and that's what I want to show you that is wrong. I mean, that's not wrong, but that's not the whole story. So what I want to show is theorem 4.6. You can go look into it. It's really easy. It's really easy. It's the convergence theorem in this book. So there is I start with the convergence theory of convergence theorem of Markov-chains, famous theorem. And I want to tell you, so for the following is clear. So PAB is irreducible and aperiodic. What is the condition? What is the consequence of it? The consequence is that P to the power of R is going to be a positive matrix. So there will be an R such that P to the power of R is a positive matrix. So if it's like this, then PAB to the R, so there exists an R, and we take it R like this, at P of R, excuse me, my friend, okay, PR AB is larger than 0. So we can find that, okay, we can find that, and in a particular, we can find an R such that PR AB, by now we understand it, right? Okay, PR AB is larger than delta pi B. So there exists a delta. So it's larger than, so the whole matrix is larger than 0. It's a positive matrix. And I can set a delta 10 to the minus 17, something very small. And you will agree to me that I can satisfy this condition. Now something fantastic comes up, and I will not speak about eigenvalues in proving the convergence theorem. Okay? Even, oh wait, so now maybe it's going to be new for everybody. So now I will not use, so what I will write down is I will write down a transition matrix pi, which is the following: pi 1, pi n. So the sample space has n states, pi 1, pi n. Pi 1. Okay, so this is so I have a transition matrix, yes? No, that is a matrix. And I'm saying that for any A and B, PAB of R must be larger than some quantity delta times pi B. For any A, it has to be larger than pi B. Okay, that we can satisfy because we have a finite Markov chain. So the pi B have a finite, the pi B are all non-zero. Those that are 0, I throw them away. They're all positive because they are probabilities. Okay, so then I can just put myself below the smallest one. I get I get a little bit of leeway, and I can satisfy this condition. Okay, so now what is this transition matrix? Yes. So there is a transition matrix P, and but thank you very much. I want to prove a theorem on P. Okay? So now this is an auxiliary transition matrix. I'm just taking the notations from this famous book. So capital Pi is an auxiliary transition matrix. Okay? And what does it do? So now, that the steady state, the steady state is pi. Little pi is the little pi's. Is the little pi's. That's the steady state distribution. So what is this transition matrix capital pi? What does it do? I mean, because you have the answer to my question on does this auxiliary transition matrix do? It moves me immediately into the steady state, right? Because let's say at time t, I'm at position pi of t, okay? At time t, I'm at position a in thing, and then pi t plus 1 of a is the sum over b pi, little pi of b pi b a, okay? So motion under capital pi. I will get out of this theorem in 2 minutes. Okay, so what is it? It's pi of t pi b, but pi ba is little pi a. So this is sum over b, pi b of t is, so this is 1, okay? The sum over b, at time t I am somewhere, so the sum over b, little pi of t is 1, so this is pi a. So this auxiliary transition matrix gets me, as Patrick just said, gets me immediately into the steady state. Now what I can show is the following, or what is easy to see is the following. The transition matrix that I'm interested in, P, okay, can be written I'll have finished in 2 minutes. This is delta times pi plus theta times q. With capital pi that gets me into pi 1 pi n. We call this gets me into equilibrium immediately. Excuse me, pi to the power r. Pi to the power r is a positive matrix. Any element is larger than delta. So I take delta times this matrix plus something. So pi is equilibrium, and q is another transition matrix. Q. All right, are you still with me? So I can write, so what does it mean? Is another transition matrix, so what does it mean? It means that QAB is larger than 0, and means that the sum over B, QAB, is equal to 1. Then it's a transition matrix. So I have to go someplace, the transition matrix. So now I have P to the R is 1 minus theta. So let's look at this equation. It's a beautiful equation because it tells you I am having a transition matrix, P. I put it, it's irreducible aperiodic. I put it to the power R. I have a positive matrix. And I can decompose it into a transition matrix that gets me into equilibrium. That is in equilibrium with a probability delta. And another transition matrix. So you may not realize, yes? Can you speak up? Yes, yes, of course. I mean, it just follows that P of R is larger than delta. So this makes that all these elements are larger than zero. So from the fact that P to the power of R, the transition matrix to the power of R is a positive matrix, I can immediately, starting from that time, I can decompose the transition matrix into a piece which is capital pi, which gets me immediately into equilibrium, and another term which is. So now let me tell you, I am making, here I have T. So this is, okay, so here I'm going in T. At this time here T, I have the value R. And I'm running lots of Markov chains. Okay, I'm running many times, as you did over the last 2 days. We are running the chain. So we are running a Markov chain starting from initial configuration, check, from initial configuration, we are running. So these are Markov chains starting at t equals to 0 and moving on. What this equation tells us is that a little proportion of the Markov chains, of the runs, of my actual simulation runs, will be completely in equilibrium already. Okay? So that's a point that I want to make. So now we'll go back. That will be the subject of tomorrow. But I mean, it's, you're just starting in this field. What I'm just telling you is that we have the impression that if we have p to the power of, pi at the power of t converges towards pi, right? That we know. We have an irreducible aperiodic transition matrix, so p to the power of t will converge to t. But then you would say, well, if we stop at finite time, we make a mistake. Okay? If we are at finite time, then we are not converged yet. So at finite time, you make a mistake. So Monte Carlo is not such a good method because we always make a mistake. It's much better to be in exact solvable models. So what this equation tells you, I'm a little bit taking you very far in the modern theory. So this is a theorem from 1986. Aldous and Diaconis. So it tells you that you run for time r, and with a certain chance, you are completely in equilibrium. You are doing an exact numerical solution of the problem that you're trying to solve. So now the theorem continues that you take p to the r, and then you take it to the power of k. And then it's very easy to see that this is 1 minus theta to the power of k pi, capital Pi, plus theta to the power of k times q. So this proves very quickly. So then we can prove so then as time continues, so we go to r, then we go to 2r, we go to 4r, and the proportion of Markov chains that are completely in equilibrium increases to become, the proportion will become 1 in the limit of r times k going to infinity. So the subject of tomorrow will be, is it possible? You understand my frustration? I mean, that I'm doing Markov chain Monte Carlo, and I always think that I have a mistake. I make a mistake because I'm not at t going to infinity. So the subject of tomorrow is going to be, is it possible to find out that so if we were able to find those chains, we would be completely in equilibrium. That means we have solved the problem of sampling from the probability distribution pi exactly without mistake. And this is the argument that shows you that this is possible. So now let me continue. So that's I mean it's such a it's such a beautiful idea. So what it means in the following: if you take the same theorem and prove it in the way we are used to it, we know that irreducible aperiodic transition matrix has a single eigenvalue 1 and has other eigenvalues which are less than 1. And then you can prove that in the limit of t going to 0, the eigenvalues which are less than 1 will disappear. But then you think that for any finite time you make a mistake. And this is a much finer analysis that shows you that this is not the case. So now let me continue. Yes? I'm telling you. With probability delta, I make this thing here. Okay? I'm writing this transition matrix P of R can be written as some probability, a transition matrix which gets you immediately into equilibrium. What do you mean it contains both parts? No, yes, of course, yes. But I'm just telling you that if you were able to make this decomposition, and tomorrow we'll actually make it. What I'm telling you that a finite time transition matrix P already contains a piece of pi, of capital pi. At the moment, no. I mean, we are just starting. We are first hour. Tomorrow we'll have second hour of Markov-chain revolution. I'll show you algorithms that actually are able to get you into equilibrium at finite time with a Markov-chain. So this transition matrix, capital pi, you know it, because that's imposed, because this is the Boltzmann distribution. That is the imposed values of pi, little pi 1, little pi 2, little pi 1. Okay? Let's, yes? Let's do the following. So the question was whether I could repeat this argument. I'll repeat this argument tomorrow. Okay, let me do it like this. But what I want to test for today, I want to tell you the following. We are having a problem of a stationary distribution, little pi, which is, we can think of it as the Boltzmann distribution. So you have the Boltzmann distribution from which you want to sample. You don't know how to do that directly. Okay, so this heliport game from 2 days ago doesn't work anymore. You don't know. So what you do is you start at t equals to 0, and you impose, through your algorithm, you impose a condition such that at t going to infinity, you are sampling from this probability distribution. You understand? That's the logic. What I'm telling you is that this argument here, on top of my head, tells you that even at time r, if I'm here, you have part of the truth. So that's the truth. Okay? So you understand that p to the power infinity is going to be exactly pi. So if you run for a very long time, then you have pi. But even at finite time, you have a part of the truth in your computer. So what I will tell you tomorrow is these advanced methods to get you. I mean, even later today, if I don't do wait. Okay, last question. I'm just saying. So this is easy to show. Second step, I take it to the k. Where is it? Okay. So and then I have to do it by induction. No. It's just there is. So what so I had this positive matrix. From that positive matrix, I took out the transition matrix pi at some time, and then I did some geometric trick. It's very easy to see that then if you take this again to power of k, then you have 1 minus theta to the power of k. All right, so now I'm going to continue a little bit, if you let me, if you allow. And I go, so there is P has this 3 conditions. So you have 3 conditions. So pi, so you have the condition here, P is equal to P times capital, pi is equal to capital P. So this is the global balance condition. Let me put it here. Sum over B. This is global balance. But since 1953, that's not the condition that was used. And even today, in 99 point whatever percent of algorithms, that's not the condition that is enforced. So that's a condition, okay, say it again, that's a condition on the algorithm P given pi, which is the Boltzmann distribution. So since 1953, that's not the condition that was used. The condition that was used is the condition Pi, P from A to B is equal to pi B, P from B to A. That's called the detailed balance condition. Thank you, Mr. Chairman. Okay, so that was the condition that was used, and it was not the other condition. So that's the detailed balance condition, and this detailed balance condition is what we used on the heliport. Okay, so what we did is the following. So PAB, you understand that's I mean, let's think the heliport on a little lattice so that we don't have to go into continuous space. And that's a completely explicit matrix. If it is 0.1, then with probability 0.1, we have to go to the right. So now we write PIB like an A priori AB times AB. So this is the probability to propose the move from A to B, and that is called the filter. You'll see it later. Filter, the probability to accept the move. Okay, so now I'm a lots of P's, and he's il rigole comme un cornichon. So he's laughing because there are too many P's. But this is considered. So let me do the following. So here we were on the heliport. Okay, we were at position X. Okay, we had a little square of size delta, and A from XY is the uniform distribution in this little square delta. Okay? And can we do a little bit of mathematics now on the heliport? I mean, on this game that we played, what was the property of this A priori AB? What kind of matrix was it? In the algorithm that we programmed 2 days ago. It was a uniform matrix, but what was even more important, it was an independent matrix, but what was it? It was, in particular, it was a symmetric matrix. Okay, so the choice of, we were at position X, we proposed to go like this, and that's when this was X, this was Y, and the probability, when we were at Y, this was the probability to go to X. So we had the fact that A from this a priori probability from A to B was a symmetric matrix. And then now let me write down the last 2 equations, and then I'm done with what I wanted to do before the break. So now let's do the following. So now we have the transition matrix. We have the detailed balance condition pi A times P from A to B. We write this as A from A to B times AB has to be equal to pi B, A from B to A times P from B to A. And then if A is symmetric, okay, we can divide it. Either it's 0, then there's nothing there, or otherwise we can divide it. And then we had that pi A times PAB has to be symmetric. So then this also has to be symmetric. Has to be symmetric. If A is symmetric, then this has also be to symmetric. And if we want to satisfy detailed balance condition, so what we can do is pi A PAB is equal to the minimum of pi A and pi B. You agree with me that this equation here, so that's one choice. For example, pi A is this, and this gives us, so now I have come to the PAB is equal to the minimum of 1 pi B divided by pi A. And we have come to a famous algorithm, which is called the Metropolis algorithm, invented 1953, that started the first Markov-chain revolution. So this is Metropolis et al. 1953. So now, what we did last week, yes? So the detailed balance condition, thank you very much. So the detailed balance condition implies the global balance. So the question was, what is the relation between detailed balance and global balance? And the answer is, we'll go much more into detail on this. The answer is that the detailed balance condition implies the global balance condition. How can we see that? Well, simply, we take the sum over A. We take the sum over A. Then we have the sum over B. Pi A is equal to the sum over B PAB, which must be equal to 1. The probability to go somewhere must be 1. So pi A times the sum over B PIB is equal to pi B PIB, and that's this condition. So this implies that the sum over B pi A PAB, which is pi A. Thank you. Yeah. Okay. But thanks to your question, I was able to bring in this little subject. Time was up. I'm not supposed to continue. Okay, see you in 10 minutes. So maybe we get started again. Huh? Now it's better. Yeah, it's very comfortable. Oh, it's the most. I have a best time here. All right. So now, let me tell you, we had a very interesting break discussion, and this discussion can continue. So I'm always very, very happy. I must tell you, when I get email, it's not my university administration telling me to fill out a form, but one of you asking me a question or making a remark, it makes me so happy. So don't think you are bothering me if you contact me. So the same. So please get into contact. Even if so, let me just do the following. We had a discussion over the break, just to get the logic right. So we had the global balance condition, which is a necessity. Right? We have to have it. It's not completely a necessity, but we'll see it. It's a necessity in order for the so this is a necessity. We want to have the Boltzmann distribution pi as a steady state. So after this necessity, we made a choice of the detailed balance condition. This was in the break we called it choice 1. After choice 1, I call this a bad choice. We made choice 2 of a symmetric proposal matrix. Choice 2. I mean, we have to realize. I mean, this is called the razor, Occam's razor. We are razor. We're taking the razor and cutting up. Past practice. So here, this is choice number 2. It's not a great choice either. And then we did choice number 3, which is this one. So that's choice 3. So now, that was what many people did. And then, of course, if you go against these choices, then you have problems getting your papers accepted. But then you can make progress. So now let me do the following. So one of you, yes. I'll tell you. That's why I'm here. That's why we are here, to discuss why this is not good enough. So, but let's first discuss the connection with equilibrium statistical mechanics. So the connection with equilibrium statistical mechanics is that usually we call pi of x is proportional to e to the minus beta u of x. Okay, so that's just a reformulation. Pi is a positive, is a non-negative function. We can write it as an exponential without going into complex numbers. So we have pi of x is e to the minus u of x. So what we had on the heliport, on the square, here was -1, here was 1, -1, 1 in y and x. Let me add a little. Okay, so this is the width delta. Okay, so this is delta. So here I am at 1 plus delta, 1 minus delta. So what I did is the following. I said that the energy here is 0. The energy here is infinite outside. Okay, so this looks like the swimming pool in Hotel Carlotta. If you look outside from, so that's like a swimming pool. So energy 0, energy infinite up here. And so that's the statistical mechanics. So, and then what we were doing is we were doing detailed balance. You can look it up yourself. I mean, then we did some dynamics that was doing detailed balance in this pool here. So now, why is detailed balance the choice that everybody has used? It is simply you are at x, position x, you go to y. Okay, so what's a good algorithm? Well, you evaluate pi a, pi b, you take the minimum of a, and immediately you have a transition matrix P from A to B. But let me go more into detail. So what is the dynamics that we had here? So we started here in the clubhouse, here at 1-1. We started here, we moved here. Then some of you ran all night, right? Is the value of pi, is it confirmed? How long did you run it? Oh, you have to say that. Now I'm getting. So why didn't you run it for an hour, for 10 hours? It was Hotel Carlotta providing electricity. It was completely free. All right. So there was no mistake that you discovered here. So, but now let me say the following. So now you run it for a long time, and what is happening is you have so for example, at some time. So you ran it, and you were at A, and so at time t you were at A, at time t plus 1 you were at B. Okay, so what is the what is the probability that in this whole trajectory in the infinite time limit, we actually saw a little piece. What's the probability to see you at time t, almost infinity, AB? What is the probability that we saw this thing here? You understand that we saw this trajectory, this little piece of trajectory? Well, it's pi a. That's the probability that we were at a times p from a to b. So we see this thing here with pi of a times p from a to b. What does the detailed balance condition tell us? Is that somebody else who runs it will see the inverse trajectory. So pi a p of ab is the probability with which you see this trajectory from a to b. Pi b p from b to a is the probability that you see the time reversed trajectory from b to a. So we had an algorithm that satisfies a detailed balance condition, and the detailed balance condition is exactly the same thing as a reversible Markov chain. So we understand that detailed balance. So if these two are the same, pi a, so that is the probability which you see the arc from a to b. This is the probability with which you see the arc from b to a, and if they are the same, then yes. So now we remember what we learned in our lectures on equilibrium and non-equilibrium statistical mechanics. We understand that in equilibrium, we have no drift. We have absolutely no drift. In equilibrium, the only motion that exists usually is diffusion, right? Because if we had the drift, then we were not in equilibrium. Equilibrium is the state, as Feynman said, when corrosion hasn't set in and when all large-scale motion has come to stop. But I mean, how are we going? What we want to do is we want to go through phase space, excuse me, where are you? Through sample space. Here you are, right? We want to go through sample space as fast as possible. That's what we want to do. How are we going to, right? That's what we want to do. You understand that? We want to move as fast as possible through sample space. How are we going to move through sample space fast if we only have diffusion? Right? And in an audience less expert than you are, I would bring out my example of coffee and sugar, and so you understand, mixing the sugar in coffee goes better with a spoon, and if you have flow, but if you have no flow, the problem with choice one, is you have abolished drift in sample space. Okay, and so that's what we want to study now. But first of all, let me give you, having discussed this connection with equilibrium dynamic, let me give you some examples of algorithms that are reversible, and you understand that a reversible Markov chain, that I haven't discussed in detail, but a reversible Markov chain is a Markov chain that satisfies detailed balance, because the dynamics will be time reversible. A non-reversible Markov chain is a Markov chain that satisfies the global balance condition but breaks the detailed balance condition. And now I see Gabriele smiling because we wrote the paper just last year, because we have some algorithms and nobody believes us that what we are doing is correct. So we did it in a very, very simple. So for those enthusiasts among you, just contact Gabriele and he'll show you the paper that has 13 5-line programs that nobody understands. And I will just give you 3 of them, or 4 of them, or I think 3. And the rest of it can be, so this is in, so we put this in American Journal of Physics 2024. It is 13 algorithms. And since we are a little bit superstitious, we started with algorithm 0. And then it's algorithm 0, 1, 2, 3, 4, 5, 6, 7 until 12. And then, if you absolutely want more algorithms, then do it. So they are very simple. So let's do the following. So the algorithm was the following. We have a u, which was just x squared plus 1/4 x4. So we have so it's 13 algorithms on an energy u of x, u of x. So when the organizers here of GGI heard about this paper, they retracted the invitation for me to come here. But then they said, well, okay, let him talk again. Anyway, so it's 13. It's a little bit crazy, but we do this. So that's this. And pi of x. What is pi of x? Is e to the 1/2 x squared plus 1/4 x4. So it's an anharmonic oscillator, and we are trying to sample the Boltzmann distribution of this, having made this connection, we are trying to sample pi of x for the anharmonic oscillator. And of these, I only give 3 algorithms. So first algorithm is Metropolis. So the pi of x is some function. So this is pi of x. Okay, it's e to the minus 1/2 x squared plus 1/4 x4. So it's maximum at 0. It decays faster than a Gaussian. It's not a Gaussian. And then we can play around with this algorithm. So algorithm Metropolis dot pi. You can program it yourself. You can also look at it. We have, as with all our papers, we have an open source directory, and you can look into it. So now the algorithm is the following. I just show you one step, input x. So the world expert is sitting back here on the left, so you can ask him. Minus delta. X prime is x plus delta. Upsilon is run from 0 to 1. And now what we do, if upsilon is less than the minimum of 1, pi of x prime divided by pi of x, then x going to x prime. And the final line of this algorithm let me put it on the same line. Yeah, it's a little okay. Then I do here output. Okay, so these are 5 lines. It's really simple, right? So that's 1953 status of. So is this a correct algorithm? So I start with x, I get x. Then I put it back in. You have to write a little loop, run it 1 million times. From x to x prime, x to x prime, x to x prime, x to x prime, x to x prime. What is going to be the histogram of the position? So if you do a histogram of positions, it will be this function up there. Okay, it's kind of very, very simple. You understand what I'm doing here? So here, so this is the a priori probability A of x prime is symmetric. You agree with that? Right, so if I'm at x, I propose going from x to x plus delta x, x minus delta x. If I'm x prime, I'm proposing the same. And the A of x prime is exactly the same as A from x prime x by x. So I can move with the probability, the acceptance probability from x to x prime is the minimum of this, and that is what is implemented here with this random variable. So this random number epsilon goes from 0 to 1, and it is smaller than 1 with probability min of 1 x prime x. Okay, so that's kind of that's not worth more than so. And this is exactly we are using the same connection to statistical mechanics. Now let me move ahead by 4 decades. Let me show an algorithm that we call a procedure. And forgive me the name. Don't ask me why it is called this. Lifted metropolis. Now watch out. So this is an algorithm from year 2000. Written by, it's a diaconus Holmes and Niels, famous statisticians. So let's do another algorithm on the same problem. Input. Okay, so this is the algorithm Metropolis. And this is another algorithm. Input x sigma. Sigma is plus or minus 1. Delta. Patrick, are you listening to me? Are you listening? You have to say now in 1 second that I have a misprint, okay? Run from 0 delta. Okay. Here I had a run of minus delta delta. Now I have a run from 0 delta. Huh? A little delta, excuse me. Okay, so now I take a random of 0 to little delta. I only move in positive direction. And x prime is x plus sigma times delta. Epsilon is run from 0 to 1. And now, if epsilon less than minimum of 1, pi of x prime divided by pi of x, then x to x prime. Okay, else sigma going to minus sigma. Minus sigma going to sigma. Output explication de texte. Okay, so this is my potential U. Metropolis algorithm. What does it do? Time goes up here. I'm here. I make a diffusion. Okay, that's the Metropolis algorithm. I make a diffusion. And the detailed balance condition is such that the flow from x to x prime, so when you do this trajectory, with exactly the same probability, you'll notice that you move from x to x prime, as later on you moved from x prime to x. That's the detailed balance condition of 1953. That's the Metropolis algorithm. And you know, it costs nothing to actually program it once again, right? And then you send me a little email, makes me happy, makes me get over my cold that I'm. So it's completely algorithm, you know. So but it's a diffusive algorithm, okay? It's a diffusive algorithm because it's actually a finite delta implementation of diffusive motion in a potential. So then you reject, you accept, and you make it such that this move and this move completely cancels. Yes? Well, there should be a for loop here. You know, so this output is the new input. Okay, so this output is the new input. Output is the new input. You get this. You get the idea, right? So I mean, you know, that's economy of. All right. So now we have the other algorithm. T. I mean, it's the same picture. So now we are U here. We start here with sigma plus 1. So what, Mr. Chairman, how are we doing with time? Yes. All right. 25 minutes. You know. All right. Okay, so we have a sigma which is plus minus plus 1. So I'm proposing a move in direction. What am I going to do? Delta is quite small. Just run through the algorithm. So I'm moving from x. I'm proposing the move from x to x prime. What am I going to do? Am I going to reject that move? No. So what I'm doing is I'm starting here and I'm accepting the move, right? Because pi of x prime is larger than 1, so I accept the move with probability 1. Then I move here. So here is 0. Then I move here. Then I move here. Then I move here. Then I move here. So now I reject the move. Let's say at some point I move. What do I do if I reject the move? I stay on the configuration, but I change sigma. So here I go up. So I had the configuration x plus 1, and I move from x plus 1 to x minus 1, and then okay. So is this a detailed balance algorithm? Huh? Yes, no, maybe. Irrelevant question. Okay, is this a detailed balance algorithm? So what is the sample? So let's if we don't answer the question, so then we go back to what is the sample space in the Metropolis algorithm? X are taken from which? Huh? Back there, what is the sample space of the Metropolis algorithm? Huh? Real numbers. Okay. Is real numbers. Is that correct? Yes. What is the sample space of this other algorithm? It is sample space of this lifted Metropolis algorithm is R cross minus 1, 1. You allow me to write it like this? So it's in some sense it's called a lifted algorithm because we have lifted, so we have two copies of the algorithm. So now what is the following is that so this in large sample space, the algorithm is manifestly non-reversible. Okay, so because we can go from x sigma to x prime sigma, but we cannot go from x prime sigma to x sigma. So this is a non-reversible algorithm. Algorithm in omega lifted metropolis. So in omega, which is r times minus 1, 1. So it will move ballistically. It will move ballistically from a configuration that it doesn't like, moves over, and goes like that. So now I could bore you. I mean, excuse me. So this is what Fabian Esler said. So we could go through a proof. We could go through the proof, but maybe we do this tomorrow, or we do this, or you do it on your own. So you have to prove that the flow into each configuration. You have to know that the detailed bands, the global bands condition is satisfied. But I think what is much more fun is to program this algorithm, right? 5 lines, and to check that against all odds, the histogram will be exactly the same histogram as before. So just program it, 5 lines, or ask Gabriele, he will, una bira, right? And you give out the algorithm, right? So you can do that. So you can program it, and we can show later that it actually satisfies the global balance condition. And so you run this algorithm. It's completely. I mean, I hope you understand that this is, this is not von Neumann algebra, but it's completely mind-boggling, nevertheless, because we have an algorithm that moves from here to here, then it moves back, then it moves back, then it moves back. It zigzags through space, and at the end, it will have the same probability distribution as before. So now to finish the algorithm, so this was algorithm number 2. So it goes up to 12 if you want to see more of them in our paper. But now let's do another algorithm. Let us take the limit of little delta going to 0. Okay, so we discussed before on the heliport that little delta was not a good idea, right? I mean, if we moved, and if you throw, I think 10 of you programmed the algorithm. If you take delta is equal to 10 to the minus 5, you wouldn't have made it in time for the lecture, right? I mean, it's just once. So little delta was a bad idea. You understand that, right? You just move to. So let's do the same. Let's use this bad idea and show that it's a fantastic idea. So now let us program this algorithm with delta smaller and smaller. 10 to the minus 17, 10 to the minus 29. We actually take the t going to 0 limit. I mean, this delta going to 0 limit. Okay, we do it. Let us take the delta equals 0 limit. Let's do the following. And I do a version where delta is equal to delta. So what I'm doing is I'm taking a grid. Okay, I'm taking a grid. You understand? I'm taking a grid of 10 to the minus 15, and then I move by 10 to the minus 15, or don't move and move back. So what is the probability to accept the move? So I'm starting here, let's say here, I'm in my potential. I start here at x, and sigma is equal to +1. So I start with a configuration time where x times sigma is negative. And now I do the following. I'm starting here. And the next move, what is it going to be? It's going to be accepted, right? I only move by 10 to minus 17. The next move will be accepted. accept it, accept it, accept it, accept it, accept it, accept it, accept it. But you know me well enough to understand that I'm not going to actually program something with 10 to the minus 17. So let's do it analytically. So what is the probability? The following. So you understand that up to here we'll accept all the moves. We'll go, we'll go, we'll go, we'll go. And up to x equals to 0, we accept the move. You understand that, right? So that's kind of easy. Job done, right? So now we continue. And I'm asking a question. What is the probability that at an x that I call x event, I reject the move for the first time? You understand? So I'm not going to program actually the algorithm. I'm going to ask another question is, you know, what I'm going to try to sample the point at which I'm going to reject the move for the first time. Right, that itself was a big revolution in physics in the 1980s when people understood that they could do this. So you understand that XEV is a random variable. It has a probability distribution. Okay? In what? That's what you think. But then there were some people, Peters and DeWitt. So this is what I'm telling you here is a 2012 algorithm that we would have liked to find ourselves, but we didn't. But so this is now we moved from 1953 to 2012. Peters and DeWitt. Very, very simple. It's just the algorithm, this algorithm that I just put here in the limit delta going to 0 in an event-driven formulation. So now what is the probability I move? So let's do the following. Let's move here, let's start at 0 because at 0 actually things start getting interesting, right? So at 0 things get interesting. So now what is the probability that XEV is the probability? And I'll prove you wrong, because I'll show you what is actually happening. So what's happening is I accept the first move. What do I accept it? Well, I accept it with pi of x prime divided by pi of x. What is pi of x prime divided by pi of x? It's e to the minus delta u. Right? It's e to the minus u of x prime minus e to the minus u of x. So it's e to the minus delta u. So the first move, so I start at 0. The first move, I'm going to accept it with e to the minus delta u. At that x. The next move, I'll accept it with u. And I'll accept all of them with e to the minus delta u. But at x event, I reject the move. So with which probability do I reject the move? 1 minus, so I reject it with 1 minus e to the minus delta u. So here, so let me just say it like this. So this is, I start here. I have a delta u, which is this delta u, which is not the same delta u as it. So this delta u is the delta u from here. This delta u is the delta u from here. So each of these delta u's are different, okay? And then I reject the u with e to the minus delta u of r, of x event. All right, so what does it mean? It's e to the minus u. So here at x event, I'm at x event, I'm at u, which is u of x event. So it is, in this simple example, it's e to the minus u of x event times delta x. No, it's delta x. What is, expand this power, what is it? Delta u is, it's du, it's delta u, it's times du. That's what it's not dx, it's du, okay? So here it's, so du. So the probability to stop at x event is e to the minus u of x event du. How do we sample that? You know how to do that? Yes. How do you sample u? Speak up. Or somebody else? How do you sample it? That's an exponential distribution. U. How do you sample u? How you sample this exponential distribution? Yeah, so what did I show? Huh? How do I sample an exponential random variable? Thank you. So the answer was the u at which I stop is minus log of random of 0, 1. Right? So this brings me to my new algorithm. So what I have to do is the following. I have to run. Then I have to take a minus log of run u, and that's up to where I go. And then I move back. How am I doing? Under the condition that my lifted metropolis algorithm is correct. Right? We haven't proven it. So if the lifted algorithm is correct, then this algorithm that I'm going to show you is also correct. It's called the zigzag algorithm. It's the following. You enter x of and sigma and then t. I enter it such that x times sigma is less than 0. So I am just overshot in this direction, and then I overshoot in the other direction, and then, yes? First things first, okay? Let's do, I mean, what I'm telling you is the beginning of a whole field of computational statistics called piecewise deterministic Markov chains. And after having solved this problem, we also solved your problem. But let's do first things first. Let's do this thing first. So we just we just want to solve this little problem and want to be sure that we actually understand what we're doing. Then we check that it's okay. And then tomorrow we can take your case, but it's kind of very easy to do. Okay, so now let's write the algorithm. So x sigma. So now what I'm doing is I'm saying that the x event is sigma times so what I'm doing is the following. I have u, which is x squared over 2 plus x4 over 4 is equal to minus log run of 0, 1. I write this as u squared over 2 plus u over 2 plus u squared over 4 is equal to minus log run. Then I have a quadratic equation, okay? When we wrote the paper, we discussed for a long time whether we should put this solution of the quadratic equation into the paper. Then I told, because I'm kind of senior, I told him, you should never underestimate in the paper that you will write if you put something that people can actually follow, and that maybe they even know. So you know how to solve this quadratic equation in U, right? It's minus b plus minus square root of b squared minus 4ac divided by 2. And you do it, and you find this solution, unless I've made a mistake. Okay? But Patrick and Gabriele will tell me. So that's the X event. Then you take a random number, run between, no, it's not like this. Then the following, you do the following, then for t star is equal to t plus x event minus x. And then I'll explain this here in just a moment. T star is equal to int of t plus 1 up to int of t event. Just a moment. And then what you do at the end, x is equal to x event. Sigma is minus sigma. And you output and t. All right, so that's, okay, so here the only thing that's a little mysterious is why do I do this here? Okay, so the thing is I'm running here like this, I'm running like a roadrunner like this. And now in order to sample just for simplicity, I put a little grid of equally spaced times, and I'm making a histogram of this x, 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 of this x. Okay, and the histogram of these things, you can do this much better. You understand what I'm doing here? Right. So it's so this is, so this plus this, these two lines are the sampling algorithm for x event given by x event given by x event given by x event given by x event. Then I road run through the space, and I tell you that the histogram of these things that you print here is going to be exactly minus e to the minus x squared over 2 minus x4 over 4. So that's the zigzag algorithm. And of course, you are invited to play around with this. Huh? The T star is, so here I'm doing the following. It's just the very, you know, the simplicity is everything. So what I'm doing here is I'm taking just, so here is time 0, 1, 2, 3, 4, 5, 6, 7, 8. So at integer times, just in this little example, I'm always checking where am I at integer times of my Markov chain. And these positions at integer times, t equals to 0, 1, 2, 3, that's what I put into the histogram. Yes? No, T star. It should be T star, excuse me, T star is T plus, no, let me see, just a moment. What was it? Help. It's T event. It's T event. T event. Okay. All right, excuse me. Okay, so that's, so at X event, I'll reach the point X event at T event if I suppose that I have a velocity of 1. So here I suppose I have a velocity, I made a little rescaling, the velocity is equal to 1, and here I'm at X event at time T event. Excuse me. So besides that, So these are kind of, yes? It's coming to an end and we have to part. But maybe, yes, okay, all right, yes. Just two few words, closing words. Few more minutes, okay. So if I have a few more minutes, so what is the algorithm is the following. I compute what is X event. X event is on the other side of the present X, and I compute the X event. I'm computing the time. So there's a little thing. So these are 5 lines. You can spend a little time checking that these 5 lines are correct. I think they are correct. Are they correct now? More or less, right? So these are correct, and then you have a fantastic algorithm that is the beginning of the field of piecewise. So you have a deterministic motion with velocity 1. It goes up to a certain point, then it moves around. You have a piecewise deterministic motion in continuous time. So in one time step, we've moved from Markov chains to Markov processes, if you want to. That's called a Markov process. And what is really surprising, it is that it samples the Boltzmann distribution exactly without any error. And it takes the delta to 0 limit without so we only need, so you see, we only need a random variable here. We need a random variable here. We need a random variable here, and we have. Okay, so it opens up. Of course, we are just doing the beginning, but it opens up endless possibilities for fantastic algorithms which are non-reversible and which sample exactly the Boltzmann distribution. So I had lots more to do, but let me just write down the title of next time. So that kind of fixes what I'm going to do next time. So the title for next time is going to be the mixing time. Okay, so next tomorrow. So it would be really fun if you could get interested in this and could actually write these programs. I think there are people in this audience who until Monday had never written a Markov-chain Monte Carlo algorithm, right? Is that true? I'm not going to ask you to raise hands, but I think it's true that some people had never written a Markov-chain Monte Carlo algorithm, and this little thing on the heliport was a beginning for you. So now you have the chance of writing at the same time your first non-reversible Markov chain, and even the first non-reversible Markov process, which is the zigzag algorithm, and even the first non-reversible piecewise deterministic Markov process. Once you have programmed that, you have nothing more to fear. And once you have programmed this, you have nothing more to fear, and you are ready for next chapter, which is the mixing time. So the mixing time is again, I will do that next time. Mixing time is again was a big surprise. 1986. That's the beginning, what I call the beginning of the second Markov chain revolution. It's the mixing time. It's trying to find out what is the relevant time scale on which you actually approach equilibrium. Until that time, everybody said, well, it's the gap of the transition matrix, right? It's the gap of the transition matrix which sets the time scale. I wrote that, unfortunately, into my 2006 book. So now I have to rewrite it and get a second edition, because I wrote my book, telling a story, my life story is that I wrote my book. I got an email from Professor Percy Diaconis, famous statistician. He invited me to Stanford. Said, your book is really fantastic, but there's a little detail that you missed. Then he gave me the book, and then he said, well, the little detail that you that you didn't put in, I didn't say it like that. He took me to a nice restaurant. It was just like it. And then he said, well, the inverse gap is not everything. There's something else that we discovered just recently. And it's true. It's true that the relevant time scale is not the inverse gap of the transition matrix for the specialist. It's something much more interesting. It's called the mixing time, and we'll discuss that next tomorrow at 11 if you want to be with me, and we'll do that. Okay, thank you.